All right, folks. So let's get started. So today's session, what I want to do was, so I was following the discussion that happened last session, and we talked about the four-sum question. Like we took the two-sum, made it, got it into a three-sum, and then finally we got it into the four-sum. And one of the challenges that we thought, that I thought was discussed but not really kind of bottomed out, was how do you deal with like the same like duplicates? So are folks clear with the solution that was discussed on Foursome?
I came up with a solution.
Okay.
What I did, and that is, I iterated through my array, with the n squared, which is I and j, and I created a hash map with the key as the integer, which was the sum of the pair, and then and that was the key to an array list of hash set of integer. So basically, you could have more than one pair that adds up to the same sum. And so basically, I went through, and then of course you can have. So my key is the sum of a pair, and I stored their indices in the hash set, and then I have an array list of the hash sets of any possibilities I find. Then I go through the array again and calculate the difference of my pair, and then I go to my hash map and try and get anything and see if I have anything, and then if I have, then of course I can look in my hash sets and see if they contain my current indices at all, and if they do, then I don't count that as a solution. Otherwise, then I instantiate an array and send off the solution. Otherwise, I return null. So that was what I came up with.
So far, I think it makes sense at a high level. So let me just restate it for folks who are trying to follow along. I am on the Etherpad just typing the steps as well so that we can go through it. You should be able to see it on the video.
Okay.
So first step, you are
actually,
go on, Pamela.
May I write?
Yeah, go ahead. All yours.
Okay. Okay. And I am appropriately pink this week. Oh God, violently pink.
Okay. So anybody else with a question around this approach? Or we can just wait and watch and see, make sure that we get it right.
Okay.
The key is integer, which makes sense, which is essentially represents the sum of the pairs of digits, or pairs of integers. Right. And the value is interesting. I see that you're using an array list of a hash set of integers. Essentially, it's a tuple, right? The hash set will be a tuple.
Exactly. It'll be your two indices that added up to that. And the reason I have the array list is you could end up with more than one possibility.
Correct.
With matching to that sum.
That is correct.
Yeah, and then of course you've got to iterate.
So when you go through this again, how do you actually eliminate the duplicates?
Okay. Well, number one, I take the difference from my t of my pair. So I generate a difference. Okay.
Go on.
And this is sorry. This is I'm just putting that down, and then
So while folks are there, I am muting people who are actually getting some background noise. So just check before you start speaking. If you're not able to hear you, probably your mic is on mute. You should be able to unmute yourself when you want to speak. And in terms of the screen, we are on the shared Etherpad, so please make sure that you are on the Etherpad as well, because that's where Pamela's typing. So you would go through the pairs and make sure that neither of the tuples that you are currently consuming is there.
Well, basically, then I would calculate the difference. I would try to retrieve it from the hash map.
You'll get a list.
A list of
Tuples.
Yeah. Well, hash said integer, but yeah. Then I just basically say if it doesn't. That, in a nutshell, is it?
Yep, that's right. That is correct. And you may have multiple solutions as well. So if you go through the array list, you'll have to just go more than that. That's about it.
Well,
so
I may have multiple solutions, but it says return a solution. So
return a solution. That is correct. So again, in case you are asked to find all solutions, or in case you are asked to enumerate everything, then you could potentially just continue your approach without having to stop, and it will still work for all of them, which is good. Awesome. So this was something that was kind of, I think in the interest of time and interest of moving on, we just did not want to spend too much time on Foursome, but I thought it's an interesting variation. How would you do 6 sum?
I had a question. So based on this solution which is proposed, the hash map solution, so what is the overall time complexity?
In order of n squared.
Who just spoke?
Pamela.
This is Vaibhav.
No. Hey, Vaibhav. Yeah, so it is, it would be n square, because as n square in terms of space, and it is n square in terms of time, because what you're doing is you're actually going through pairs of numbers. So that's n square already, right? The cost of actually finding pairs of numbers in an array is n square, because for every number you have to check with every other number. That's how you make a pair. And you are putting it in a hash set, and that hash set also will store essentially n square elements. And then when you're going through the second pass, as she was talking about in the essentially in the steps 2 and go through all possible pairs, and in step 1, actually, I don't know why it actually repeats step 1 twice, but sure. First you create hash map, and then in step 1 it becomes again you're going through every key one more time, so it's n square.
Right. So like the last time around in the two-sum problem, we had discussed a solution without any space, which was n log n. So when we sort the array and use 2 pointers from both ends, we have an n log n solution, right? So I was wondering if that could be extended here to a foursome. So if we like
yes, you can. Yes, you can. And that solution was what was discussed in a last class, and we kind of briefly touched upon the hash map based solution, but when collisions came up, we just kind of walked on to a different thing and we moved on. So just to kind of summarize that solution, what you do is you create a sorted array first. The cost of sorting an array is
n log n.
It's n log n sorting, right? So it's n log n. Now what you want to do is you want to assume that one of the answers is the first element, and then you want to find its complementary pair on the right hand side. And to find the complementary pair on the right hand side is a binary search, right? Because it's a sorted array. So that will take you that will cost you log n for the first element. If you're not able to find an answer, then you assume that the second element is an answer, and you try to find its complementary pair on the right hand side, and so on. So for each of the n elements, you will actually be performing a log n operation. So that is another n log n. So sorting is n log n, and the search operation is n log n. So that's how you do the two sum. for the threesome, you assume that the first element is the answer, and you perform a two-sum on the remaining array.
Okay, so
And
like instead of
that will be n square log n.
yeah,
Go ahead, brother.
instead of the two sum, instead of performing binary search by fixing one element at a time, so I believe we had discussed a solution where we have 2 pointers from both ends. So that way we had it is just each time it is instead of n log n, the overall complexity would be only n. So n time plus sorting time, so overall it does remain n log n. So I was wondering if for the foursome we can do something like fix 2 elements at a time after sorting the array and perform a two sum on the remaining array. So that way we'll get n square log n overall.
You're still n squared. Yeah. One issue I did have with a sorted array, and it's just a nit, but it said return the indices. And the trouble is, once you sort the array, the indices change.
You could save the original index along after sort. While you sort, think of it like a sorted hash map or something like that, where the key is the actual constant and the value is the actual index. So you could store auxiliary data and make it happen.
Well, you could, but I just wanted to bring that up. It's not so simplistic as stated. You know, you've got that little issue that your indices change during the sort.
Correct. So if you're on the Etherpad, what you'd see is that essentially what you can do is your sorting complexity is n log n, and then your two-sum operation, by just doing the left and right, you can get it in O of n, correct?
Right.
Then the three-sum, essentially you don't have a choice but to actually fix the first element and perform a two-sum on the remaining, and you could do a two-sum in O of n, so in n square you should be able to account for that, for three-sum. It's n square plus the cost of sorting, but cost of sorting will melt in the size of the three-sum problem. For foursome, it will be similar, which is n times a three-sum problem, which is n cubed now. So the sorting and seeking solution is actually an n cubed solution, not an n square. So the n square is our current solution that Pamela just discussed is actually superior in terms of time complexity, but not in terms of space complexity, because the n square solution uses O of n square space, whereas the n cube solution actually uses O of n space if the array is immutable, and it uses O of 1 space. Essentially, if the array, you can destroy the array by sorting. All right?
Okay, yeah, that makes sense. Yeah, thanks.
Okay. And it extends the same way. So 5-sum would be n power 4 and so on. So I mean, in general, like, you know, a k sum should be equals n power k minus 1, I believe. That's a generic form of this equation. How would you do 6-sum? A 6-sum would be n power 5 using this algorithm, but how would you do a 6-sum better than that? Any takers? Anyone at all? Come on.
Break it into like 2 3-sum problems. Like if 6-sum by 2 is actually a 3-sum problem, and
correct. So just like how you did n square, you create all pairs of integers, you did the operation. You could actually create cubes of integers, or like or take 3 integers at a time and add them up. So it's identical to the foursome algorithm, except that the cost of creating it is n cube, the space you need is n cube, right? And then you will actually use another n cube pass essentially to figure it out. So net of it is n cube.
Hi,
right?
I had a question.
Good.
Yeah, I had a question about the foursome problem. So if you generate all pairs in n squared time and then sort it in n log n and run from each side using n, isn't it n squared plus n log n plus n?
That's a fantastic question. Can somebody else take a crack at it? So who is speaking? By the way, I just missed your name.
This is Roger.
Who?
All right.
Okay.
This is
Raja.
Roger.
Raja, can you repeat your question?
I'll repeat the question. So the question is that if instead of the two-sum algorithm of actually trying to do the lookup, what he's asking is that can I not sort the n square array, right? And then do a parallel, like left-right scan.
Right.
Correct. So the first thing is that given the fact that the elements are already in a hash map, you're only going through the entire array once, and that's O of n square for the scanning. Right? Okay. Now, so that's what you're doing this way. So your parallel scan algorithm is not going to be any different. But that being said, what is the time complexity of sorting an array of size n square?
Of n square log
n square log n square.
log n.
Which is
N square.
What is that? It's n square log n square. What is that?
N cube. Okay. Okay.
No, it's not n cube. That actually translates to n square
log n.
Log n times 2. Essentially, it's 2 times. The 2 comes out in log. So the 2 goes away because its constants don't matter. So essentially, the time complexity is not n log n for sorting. Time complexity is n log n only when the number of elements is n. If the number of elements is more, then you have to figure it out. Okay. All right.
Right. Yeah. Thank you.
Hey, Vishwa, I think I'm not able to unmute you for some reason. I think it looks like you have muted from your side. I would just sorry about that. I would recommend that I think you should be able to unmute yourself, but for some reason I'm not able to unmute you. Yeah, there you go. Now you should be able to speak. All right.
Okay.
Yeah, there was a little bit of background noise, so I had to trim you off. Cool. So the unmute doesn't work the way I thought it worked. All right. So this is good. I think this is a great. This is the discussion that I wanted to have just to make sure that we understand how to deal with the four-sum question. So six-sum works the same way. Like in any even numbered sum, what you need to do is essentially create a combinatoric array of that. If you want to do 100 sum, you will essentially create a n power 50 array, taking all combinations of 50 and then essentially doing a 2-sum equivalent on that array, and it will work. How would you do 5-sum? Now that you've done 4-sum, 6-sum, even numbers are easy. How do you do a weird number like 5?
You have to do a 4-sum and then go through the sum minus the 4-sum, right?
You could do that, or you could do a 3-sum and a 2-sum, and then you could compare them. So the purpose of this exercise as such is like a few things, right? Number one is many folks, when they try to prepare for interviews, they just go with they get a 2-sum solution. Geeks for Geeks has that, and many other websites have it. They take a look at the 4-sum solution or the 2-sum solution, and then they're like, I'm done, and that's about it. There are like interesting complexities and extensions that you can run when you are actually thinking about how do you go from a 2-sum to a 3-sum or a 4-sum and things like that. So the idea here is for us to think about how else it can happen and also get to the complexity of those operations. So given where we are, in the interest of time, I'm going to move on, but I'm actually challenging you guys to think about how can you take the solutions that you have so far and put that together in terms of a bigger solution. Does that make sense?
Is there? I think there must be a way to do it using dynamic programming, which will drastically reduce the complexity. But yeah, let me figure out later on.
Yeah, think about it. At the face of it, it doesn't look like there would be a dynamic programming construct here. A dynamic programming construct generally involves the ability to have like a reducing problem space, but it doesn't look like there'll be one here. So that's where the challenge is. Okay.
Okay.
This doesn't lend itself to that kind of piece. So the next question I just have is, so this one was also discussed last time. I just wanted to, one area which was interesting. Go ahead.
Before we move on, I I wanted to know, like you suggested, to try out the Foursome problem. Can we better n power 4? Is that what you're saying, or n power 4 is the best we can do for Foursome?
You can do better than n power 4 for sure, because you can solve Foursome in n square, right?
Foursome you can solve in n cube, right?
N square. Pamela just had a algorithm that Pamela had is for n square.
Foursome is
n square. This one here, like lines 23 to 26, represents the sorting method. That will be n power k minus 1 in a generic scenario. Okay. Right. So this is using the sorting method. But if you use the pairs plus hash method, which is what we have, then in that case a two-sum is actually is O of n, because there's no pairing here. Not pairs, combinations. Okay. Okay. I think I can avoid the background music. And a Foursome would be essentially O of n square, and so on. So what happens is that it is k sum. If k is even, it will be O of n power k by 2. But it will occupy n power k by 2 space as well, right? And then once you have a Foursome, a 5-sum is essentially it's n times Foursome, right? So you can do a 5-sum in cube.
Yeah, basically, I think what you would do is store all of your unique sets of 4 with another diff, and then it becomes a 2-sum problem. Okay. Okay.
So this is how it will work. Now my question is that you could either do this as n times Foursome, or you could do it as a 2-sum times 3-sum essentially. Right?
Mm-hmm.
All right. So can I move on, or is anybody else with a final opportunity to ask any questions on this problem? We've got loads of other problems as well, so I don't want to keep on with the old one. All right.
Sure.
The next one is another one where we said that we are given an array of integers, and every number is between 1 to n. At least one duplicate is there. Please find out, and so on. I think we discussed lots of good solutions, but the question that was actually not answered per se was one of the interesting spins that was thrown in was to say, what if the array is immutable and you cannot fit the entire array in memory? So you can't store O of n in memory, and you cannot sort it essentially. Those are the two solutions. As a typically interviewers was going to do that, where they'll come in and add constraints or eliminate constraints to make you go away from the solution that you have already chosen. So the two solutions were discussed were thrown out when the memory constraint was added. So how would you deal with it?
So there was one solution which was suggested last time around about using a bit array. So since
if
there
you
are
can't,
n elements,
if you can't store n elements in memory, you cannot store n by 8 elements in memory as well by default. Bit array or n by 64 or whatever, right? The bit array improves your space as in doubles or quadruples or multiplies it, but it doesn't really change. It doesn't dynamically change the game, like, or dramatically change the game. So good thought, and we should definitely consider using bit arrays whenever we can. Go on.
So I think one approach would be to, like, section a certain amount of memory for the count, and the other and, like, keep writing it to disk if you don't find that, almost like using a block array system where you have a certain block in memory and rest of the numbers are on the hard disk, right? So for example,
but how do you? I don't understand that algorithm. So let's assume that for simplicity, let's assume that you can only store 10 elements in memory, right? And your array is 1,000. So you take the first 10 elements of the array and you put it in memory and do what?
Let's say you have let's say this condition, right? You have 1,000 elements and you can only take 10 elements in memory at one time. So what you could do is, like, you could break that 1,000 range into let's say by 4. So you bring in 6 elements at a time. For every element, you see what disk block would that element fall in, and if you let's say the first number is 4, so it will fall in the second disk block or something. So you bring that thing into memory and increment the count for the number 4. Essentially, you're keeping the count array in disk, and you're just you're reading in chunks of that array into memory anytime you see an element in that has to be updated in that chunk.
Fair enough. Any questions on this approach for others before I start talking?
could we do something like, I mean, this is by no means an efficient solution, but I suppose it would be a working solution. So could we do something like an external sort? So for instance, you said only 10 elements our main memory can manage. So if we sort 10 elements at a time to, into the physical memory, and at the end of the thing, once we are done sorting everything, the duplicate will be, we just need to scroll through the entire file and iterate through the entire file, and the duplicates would just be adjacent. I know the time complexity is off the charts, but it is a working solution.
In this situation, you can't do that. Yeah, Harneet, go ahead.
Yeah, another variation to what this guy suggested is, so why don't we maintain like buckets in the memory? Just maintain. Suppose we have like 10 ranges in the memory, and we just store the count. So, for example, for 1 to 10, we store a count, and for 10 to 20, we store a count, so that we cover from 1 to n plus 1. So there will be a count variable which will have more than so for 1 to 10, if the count value becomes 11, that means the number which is duplicate is between 1 to 10. Then the next
I challenge you there. What if 1 to 10 is exactly 10? There are duplicates and there are numbers missing.
Okay.
Like every 1 to 10 is 5. So obviously 1 is missing, 2 is missing, 3 is missing. All the 10 values are 5. Your counting will actually give me 10. And are you telling me? So it's deterministic one way, but not deterministic the other. So if the number of values is less than 10 or equal to 10, that does not guarantee that that every element is unique, right?
I got your point. So yeah, my solution is just for exact one duplicate. It's not for at least one duplicate. Yeah.
Correct. So, but the general concept does hold good. So what you can do is, I think this was also what folks were discussing, was that if assuming you have only space for 10, right? Only 10 elements is what you can support. Then what you need to do is try to look for duplicates, like a hash map. Create a hash map of elements from ranges 1 to 10 only. So you go through the entire array, you ignore any element that's greater than 10, you ignore any elements that's less than 1, and then you try to do just do a hash map solution for that. If there are any duplicates, then that will show up on the hash map, right?
Mm-hmm.
If there are no duplicates, then you ignore it. Then you go back to the beginning of the array. Now you do 11 to 20, and then you keep doing it. So you'll essentially run 100 passes for each of the ranges of 10 and solve it. So the number of passes you will need to do this operation is essentially your data set divided by the memory you have. It's not a pretty solution.
Well,
but
no.
It'll get the job done. But it'll get the job done, and that's
right.
kind of what. Again, if you are dealing with constraints of space, constraints of time, and all those constraints of space and limitation in terms of memory, in terms of immutability and things like that. This is sort of like a brute force-esque approach, which is still not brute force. I mean, it's a little better than brute force because you are using a limited hash map, but that's probably the best you can do. Is there anyone who has a question on this approach?
Vivek, I couldn't understand.
Like I have,
what is the solution?
Navneet here. I have another solution. Like, can't we?
Navneet, before we move on to your solution, Karthik had a question about he didn't follow the solution. So let me make sure that we repeat the solution and get that, and then we can get back. Okay. So Karthik, the solution is that if you have an array of numbers, and you are trying to find duplicates in that, right? And you cannot store, like, if the range of the numbers is like between 1 and 1000, or like forget the number of elements. The number of elements could be 10, 100, or a million. That is irrelevant in this case. But if the range of numbers is between, say, 1 to 10,000, that's what the range of numbers is. It could be 1 or it could be 10,000. What we are saying is we are trying to find if there are duplicates between 1 and 10. That's it. Okay. So you go through the entire array. If there is any duplicate in the array which is actually in the range between 1 and 10, if there are 2 5s or 2 6s or 2 7s, you will find it, right? Because you will put it in a hash map, and then you'll keep checking. That's easy.
Yes.
Okay. In the first pass, you will not find a duplicate if there's a duplicate on 15. If there are 2 15s, you will not find it because you're ignoring it completely.
Yes.
What is the memory requirement for this? The memory requirement for this is at most 10. Because you will be storing like a bit vector in this case of size 10.
Okay, yeah.
Correct. Now, if there is no duplicates found, you again go back to the beginning of the array. You repeat the process, fresh, but this time you are looking for range between 11 to 20.
Okay, got it. Okay.
And so on and so forth, right? It's not a complicated solution.
Yeah, got it.
Yeah. You will have to do 100 passes then to get to 1000, or 1000 passes if you want to get to 10,000. Right?
When I heard like it's a dynamic array, so I thought like how can we store and go through it? That's why I confused.
Got it. No worries. Before we discuss Geek's solution, Navneet's solution, anybody else with a question on this current solution?
Yeah.
It's not very intuitive.
Yeah.
Go ahead,
question I had is now what is the time complexity? Asymptotically, this is O of n square, right? So it is n into n by 10 essentially. So it is O of n square.
It's more like n log n, but sure, because the reason for that is the number of passes, you'll actually go through the entire array every time. The number of times you'll go through the array is actually the size of the array divided by the memory you have. It depends on what it is. So typically, if you look at it in terms of general analysis, I look at this as more as a log n pass. If it's 8, then it's n by 8. If it's 10, then it's n by 10, and so on. But that's again still be back to n. So it is an n square solution if you If your memory is super limited, and if your memory is considerably large but not as large as the big one, then you actually venture into the log n space.
Okay.
Right?
I just wanted to make sure that we are doing better than the brute force, even asymptotically.
You cannot, I see what you're saying. The brute force solution would be you take the first element and then you go through the whole array, and then you go to the second element, go to the array, and so on, right? So yes, this would be better than that in terms of the memory. I mean, if your memory is limited to only constant memory, right, then brute force is the only answer.
Right. Got you. Yeah. Thanks for that.
Okay.
So is the array sorted one?
No, otherwise then it becomes easy. So we had one question on the chat is that for each iteration, do you start at 1 again? No, you should not start at 1 again. You have to start from the first one. So you start 1 to 10 is the first one, 11 to 20 is the second one, because the size or the window of number of elements you're looking for has to map to the memory. So you can't go back to 1 every time, otherwise it doesn't make any sense, right? You have your window size is the same as what your memory is. Okay. Yeah. Sorry. Go ahead. What was the question? I cut somebody off.
I think I got the answer. So we take one element and traverse a complete array with the partition size, right? First we take first element, check in the 10 elements. Next, take the 11th to 28th element, like that, right?
No. Your partition is not partitioning the array, but you're partitioning the integer space. So if your array elements are between 1 and 10,000, regardless of the size of the array, your first partition will be between 0 and 1 and 10. So you create essentially you could use a Bitvector or you could use a Hashmap to do that, but you create a Bitvector and you look in the entire array if numbers from 1 to 10 are there in duplicate. If they are not there, then you go to the next partition. The next partition is a number between 11 to 20. It has no significance to the array at this point of time. You're trying to look for duplicates between 11 and 20 in the entire array. Then 21 and 30, 31 and 40, and so on. And you will essentially have to do 100 passes regardless of the size of the overall array. The array could be millions of bit integers long or billions of integers. It doesn't matter.
Sure. Got it.
Okay. All right. Navneet, you had a solution. Sorry, it took us a little while to get here. Navneet, are you there?
Sorry, my phone hit badly. So what I was thinking, can't we do a sort of a merge sort? We can do a merge sort for large files, right? Will that be efficient than doing it this way, where you, for example?
Yeah, you can. So the solution that Geek is proposing is, can I do something like a merge sort, which is sort of you partition the array into smaller chunks, and then you independently sort each of the chunks, and then as a part of the combined sort operation, you end up merging at different levels, and at some point of time you can actually detect the collision. That's not a very difficult thing to do, but it's the time complexity is not correct in that case. The space complexity is not correct. Merge sort actually expects or requires auxiliary disk space, and it is O of n in terms of space, not limited. And since you're not permitted to do in-place merge sort, it's still a problem. So I would not be, the merge sort will not be an answer based on the constraints we have. But merge sort is typically a good answer for the find duplicate because it actually gets you the answer without having to sort. You don't have to necessarily go through with the sorting operation. You can get the answer somewhere in between. I know Navneet just left, so he probably didn't hear the answer. But is it clear for the rest of you?
Mm-hmm.
All right. So let's go to the next one. This one's so now new question for today, basically, finally. So let's assume you're given a large data set of numbers. It's kind of like a complementary question to the find duplicate. It's the one that's like find missing. the array is very large. It's got millions of numbers, and it's a 64-bit integer range. So it's like large numbers, large integers, and large size. Your goal is to actually check if user IDs is already used. Actually, the first question is incorrectly worded. The first question is like, give me an user ID that is not in the system. And the second question is to check if a user ID exists. So first question is, find a number that is not in the array. Any number.
So it's like is the array the numbers are duplicated in the array or only?
No duplicates. These are user IDs. The numbers are guaranteed to be unique in the array, but they are not in sorted order.
Yeah, that's fine. Then we know the limit, right? So what is the ID limit from 1 to
64-bit
X number? So we can do XOR operation first between 1 to X, and then we do without output. We'll do the XOR operation between the array of elements. Then we find the missing one.
Good answer. If there's only one element missing, there are a lot of element numbers missing. Find one missing user ID. So the scenario is that that we were using random assignments for unique for user IDs, and now we just don't want the random anymore. So what we want to do is we want to go back and see which user IDs were missing and use the existing user IDs, because when we use random, after a point of time we start colliding, and then we have to create multiple random numbers. So we don't want to do that anymore. We just want to go back from in the array, just go find a value that is not in the array and use it. XOR works only if you have one missing element.
Yeah.
There are multiple missing here.
So for each user you can have a bit vector, bit, right?
So
is a question clear for folks?
So it's not very clear to me. Like so this is represented as one large big array. Is that the representation of the data structure?
Yes, it's an array of integers. Correct.
Okay. And like on the first question, like is it like a one-time operation, or is it like something where you're going to use it like multiple times?
First one is a one-time operation.
Okay.
These are great questions, by the way. You should always ask: is it a one-time operation, or am I going to ask this again and again? Because you could essentially do an expensive pre-compute operation and amortize the cost over the long run.
Yeah,
and in a typical computing problem, that is more common. So you would actually don't mind spending like an n cube or an n power 4 pass to prepare the data set, especially when your leading vector is not the size of the data set, but it's actually the number of calls that will eventually come.
Yeah.
So it's a great answer.
You could have a bit
that you create a large array of 2 to 64-bit ints and mark which ones have been used or not, right? If it was a repeated operation, just a dirty way of doing it.
Got it. It makes sense. Vishwa, go ahead. You had
I think it's the same thing. You just have a bit for each user ID that's used, so you mark it as used.
That will be too large for the space at 64-bit.
It's a bit, right?
Yeah, even then it will run into petabytes, I think.
Yeah, but
you have
in general, for such a question, you can use this is essentially similar to a Hashmap solution, right? What you're saying is you'll take all the user IDs, I'll put in a Hashmap.
Right.
Okay, but then how are you finding if something is missing or not?
Is that user ID length?
Okay, so the difference between a bit solution and a Hashmap solution in general is, in a Hashmap solution, what you're doing is you're only storing as many elements as are there, but in a bit vector, you're actually creating a Boolean place for every element in your range. So you should be able to iterate your bit vector and figure out what is missing. I get that.
So you mean a
Is
hash
there anyone
set?
who? Yeah, go ahead.
You mean a hash set, right? You want to store you want to take the initial cost of populating all the user IDs in a set, and then it's then a constant time check to actually see if a given user ID is present in the hash set or not, right?
Yes, that is the second question, right? The first question is actually to find a missing user ID.
Right.
And Purna, you can't assume it's a fixed length, but assume it's a reasonable length between 30-40 characters.
Right.
Or in this case, it's integer, so it's fixed length.
Okay.
The first question is actually, the question is based on user IDs are numbers, so it is a 64-bit number, so yes, it is fixed length.
Okay.
Go on.
So yeah, so I was just saying that store all the user IDs in a set, and then just check is present or not. If a user ID is present, it's just a constant time operation to retrieve the fact that it's present. Otherwise,
yeah. That's
okay.
You're answering the second question.
Oh, okay,
which is
okay.
fine, which is you can put it in a hash. If it's a Boolean test, right, is present, then it's very simple for you to get that going.
Right.
But let's go back to the first one. We're saying how do you find it's missing? One of the easiest ways you can do that is you can sort the whole array. And assume it's large, but you can sort it. And just like how you did find duplicates, you can just go through the entire array and get it.
Okay. Okay.
Does the sorting make sense?
You would actually sort, and you would want to traverse. Okay, you do then binary search to check if the user ID is present, or
correct.
Okay.
How would you? That was the first one that we were just talking about that before we started the session, right?
Right.
If you're given a sorted array, how do you find something that's missing? Is you go to the midpoint and you look at the array ID at the value at the midpoint. It will either be equal or it will be less than the index.
Right.
If all users to the left of it are existing, then the midpoint index will be the same as the midpoint value. If there are some numbers missing, then the midpoint index will be less than the value in midpoint because there will be a greater user ID there. So that way you know that something to the left is missing. So you can eliminate the left half, or you can just focus on the left half, depending on what is the value of A of the midpoint, right?
So just restating what you say, if A of I is greater than I itself, that means there is something missing.
Missing to the left, missing between 0 and A of I.
Correct. Okay.
Right. So that's the solution. I think Nanya, I just saw your comment about 10 minutes ago, and unfortunately it's out of context now, so I can't go back, but we'll probably cover that again at some point in this case. So we can do that. So that's like it's a standard problem. It's very similar to the find duplicate and find missing, are sort of complementary in some ways. But what can you change in the algorithm if you are actually okay? Yeah. So two questions here, Nanya. The first one is. Three questions actually. The first question here is find a missing user ID from this list, and you're not given the user ID at all. So find any user ID that is missing. The second question is, given a user ID, test if it's present in the list or not. So for the first one, the way we are trying to solve it is we want to sort the whole thing and start linearly scanning from the beginning, or we can use a binary search algorithm. Either one is fine. And time complexity is different. In one case it's O of n, in the other case it is O of log n, with the amortized cost of sorting upfront. The second scenario is put the whole thing in a hash set, Bitvector, or whatever that would be, and use that to figure out if something is there or not, and that's a quick test. So far with me?
Mm-hmm.
Okay.
Priya? Hello?
Go ahead.
Yeah, so I understood the first part where you were telling that, it's you do a linear search. Could you just repeat the binary search aspect of it, since we do not have a user ID already in place? How did we do the binary search? What did we just had a midpoint, and then how did we go about looking for the missing user ID?
Fantastic question. So here's what happens, right? So if I give you, first thing, you just go to the midpoint, okay, and you compare the index of the midpoint with the value of the midpoint. So you check if A of I, and you compare A of I and I. Right? So what happens if, what are the possibilities? A of I cannot be less than I, right? At all. There is no way.
Okay. A of I cannot be less than I. Can you do it with an example? Let's take
Sure.
an array of 5, 4, 3, 2, 1 or something like that, or something.
So let's go to this, right? So 0, 1, 2, 3, 4, 5, 6, 7, right? So this is what we have. I'm on line 45 on the Etherpad if you're there. So this is also the index, right?
Right,
okay.
That's the index. That's right.
One is, this is the index, and this is the value, whichever way you can look at, slice it whichever way. So when I'm looking at the fourth element, this guy, is there any chance that the index or the element at the fourth index, the value can be less than this? Like can this be a 3? The array does not have any duplicates, we know that.
Okay.
Right? In that case, all the elements to the left has to be less than 3, and you have more spaces than the numbers. So there is practically no.
Sorted? That's what you're assuming?
Yes. Array is sorted. The binary search only works when it's sorted, right?
Correct. I understood now. Yeah, it's sorted. Obviously, it's binary search. Yeah, perfect.
Yeah. So if A of I is less than I is not possible. Okay.
Right.
A of I can be equal to I, right? What does this mean? What does this mean?
Then there's nothing missing.
No, nothing missing to the left.
Right.
Everything is right. Nothing is missing to the left. Right.
Yes.
Right.
Okay. Which means now you can just repeat the same binary search operation on the right half of the array.
Correct.
Okay. What if A of I is greater than I?
So something
what does it mean?
So something is missing on the left.
Not just something is missing. You know that
elements lesser than the index are missing, right? Okay, go ahead. Sorry, I'm sorry for interrupting. Yeah.
Oh no. Good one.
Right, the difference is missing. Perfect. Yeah.
Right. So not only do you know that something is missing, you actually know how many elements are missing.
Perfect. Yeah.
Right.
Yeah.
So, given that we know that now some number of elements are missing, we'd actually do better to search in the left half. So this is like a sort of a modification of the binary search. So if you know exactly how binary search works and you know it inside out, you should be able to take these kind of problems which are not really directly related to binary search and apply that to a searching problem, right?
Right.
Apply the binary search algorithm to this one. So is it clear now?
Yes.
Excellent. Any questions before we move on to the next one?
Yeah, you made it very clear. You made it very clear with all the 3 cases, enumerating all the 3 cases. Thanks.
Got it. Awesome. So third situation that we have here is essentially saying that what if you're okay with an imprecise answer, which means that if I say is present, if I ask for the question of user ID, I want you to return true if it's there and false if it is not there, right? Like if is user present, I want you to return true or false. False if the user is not there, and true if the user is there. You cannot return incorrectly if you can't say the user is not there when the user is there, but the opposite is okay. As in, if someone's actually think of it like, I'm trying to register for a new Gmail address. So when I search for a Gmail account and I'm just saying is sdskills@gmail.com, is it available? I get a feedback back saying that that user ID is already taken, or I get a feedback saying that user ID is available. Now, that it'll be great if it's precise, but it's okay if it's imprecise.
Recommendation also.
Yeah, leave the recommendation out for now. Let's talk about the existence or absence, right? So for the existence or absence scenario, it'll be fantastic if you can do if I can say that that deterministically you can say yes it's there or no it's not there. But it's also acceptable to have an error, right? They can tell me that this user ID is already taken, even if it is not taken. in some scenarios, not all the cases, then that will be useless. But if there is a possibility of an error or a issue with if something is missing, something is going wrong, and they can return a wrong result at some points of time in one direction, not another direction. They cannot tell me that this SD skills at Gmail is available when it is not available. That doesn't make sense. But on the other direction, they can definitely provide an error. So how would you use this information to simplify your data storage requirement? Like, how would you store the data? And this is no longer in the int domain, right? At this point, let's assume that this is more like a email address, the Gmail scenario. Did you ever get a chance to look at the handout before?
Yes.
All right. So any recommendations?
You can use a try and store all the user IDs and you can do a membership test for that.
But if you do a member, but that's still precise.
Yeah, it's still precise.
Only store a certain length of the items. So if you're looking for a string, for example, only store 8 characters, worth, even though it might be longer. That might be a precision, Yeah,
that's a fantastic answer. I mean, let's assume that you only store the first letter, just for argument's sake. Then you can only create 26 usernames. That's it, right? Like once Adam is created, Arun cannot be created because A is duplicate. It will say Arun already exists, and so on. I mean, I'm just taking it to an absurd level, but you can probably do 10 characters. You can do 20 characters. You can probably do things like alternate characters, or some mechanism of actually reducing your space from the entire list to a smaller one. Another way of looking at it is to actually do hashing. Just hash it, and hash can result in collisions. And if your hash collides with an existing element's hash, then you don't get your username. Would that not work?
You just store the bits.
This sounds like Bloom filters, right? It's similar to.
It is Bloom filters. I think I did even mention that you should think about Bloom filters. So it is Bloom filters. The first step of this is actually the easy scenario here. The first step is that if you hash it once, right, just simply hash it, what you get is a hash code, and if the hash code does not exist in your storage, then your account is guaranteed to be unique. The user ID you're checking for is guaranteed to be unique. But if the hash code exists, that does not mean that it is unique. It means one of two things, right? It means that either it exists, or it means that there exists another user ID with the same hash code, and just too bad. So this is an imprecise response, but you are actually storing less. And Pamela, your approach of storing like some lesser number of characters, cutting it down, essentially it's the same thing. What you're trying to do is you're trying to reduce the storage space of the big data into a smaller data set, and as a part of the storage you will have collisions, which in the grand scheme of things is kind of what the hash is also trying to do. But hash will offer more obscure collisions and not like literal collisions where if I keep only one letter, it will only let me use 26 email addresses. That doesn't help. So far with me? One way to make it better is, and I won't go into the details of the Bloom filter right now, but this kind of a problem or solution actually uses what is called a Bloom filter, where what you do is instead of using a hash map to store the hashing function, what you're trying to do is that you will use your function to get one numeric value, a value between, as I said, like 0 and say 100. So what you're trying to do is you will write a hash function that will give a value between 0 and 99. All right, and you will use like a bit vector, and if your hash function returns true, then you will store it in that location. If your hash function returns, whatever number it returns, you'll set that bit to true, right? That's what happens. Now, when that happens, how many unique combinations of accounts can you create now? 99, right? 100. 100, right? Because for every bit you're only associated with one account right now, and that's only 100. That's all you can do right now. What Bloom filter does is it does one better. So instead of using one hash function, let's use two hash functions. So what we will do is that if the username given is, say, SD skills, you apply hash function 1 on it and say that returns 6. And then you apply hash function 2 on it and that returns 8. Right? You set both those bits to true. That's it. Now what happens is that when I'm trying to repeat this operation, if I try again with SD skills, I can go and check in the 5th and 6th location and I will see that both of them are true, which means SD skills already exists. Right? The collision happening in one hash function is obviously pretty high given that there are only 99, but the collision happening in two hash functions is actually lesser. And collision in 3 hash functions is going to be even lesser, and so on.
So in the process, won't you end up storing lesser number of user IDs or something? Because
no, you'll store more, because in the 99, what you'll end up doing is that you can search and find the algorithm and the math behind it, but the whole idea is that there is actually a way of figuring out what is your problem space, which is n, and how many bits of data you want to store, which is m, and how many hash functions that you need, that is k. And there's like a mathematical formula with which actually tells you that given this size of bits, this is what it is and this is what the case is. What is your probability of false alarms? So as long as you are accurate 95% of the time, we are okay, and that's typically like a metric or bar that people use. So if that is the scenario, then what should be the m and k values for a given space of n? It's actually fairly small, and this is what is used in most first layer of defense. Like the most common one is used is your Chrome actually uses it to figure out if a URL is malicious or not. So what it does is that it actually has a Bloom filter cache stored in your on your computer, and then when you go to a particular URL, it checks that URL against the Bloom filter, and if it's clean, then nothing to do, no need to do anything, and you can just continue. But if it comes back as dirty, then what it does is it actually makes a web service call to the Chrome's backend systems to do a deterministic lookup, and that only happens in case of a real malicious URL or in case of a false alarm, which is okay. So that's how they use it, and it's a fantastic concept. It's not very complicated to learn, and it actually has applications in many common spaces. The very interesting aspect here is that you are able to tolerate like the lack of precision of the response, which makes it interesting.
Vivek, I had one question. So it sounds like a great solution, and it will satisfy the conditions you are looking for also. But is there any way to go back on the commitment, like if a user deletes himself? So now if I'm, like you said, 2 hash functions, 5th bit and 6th bit is set. So I would not be able to go and unset it, right? Because those could be common bits with other user IDs.
Exactly. The limitation of Bloom filter is that it does not. You can only add elements to a Bloom filter. You cannot remove elements from a Bloom filter. So if I have a Bloom filter cache or Bloom filter data store that is set, I can add more elements to it. Like I can actually enrich an existing Bloom filter of if it's representing a set of X elements. If I want to add like 10 more elements to it, I can just enrich the existing Bloom filter and add the 10 elements to it. It's very trivial. But I cannot remove any elements from it, because if the fact of removing, I do not know which elements actually contributed to the setting of those bits, right?
Right.
I have no way of knowing. So the only way to do a removal in a Bloom filter is to actually recompute the entire data set, which is which actually completely defeats the purpose. So Bloom filters are generally used only with scenarios where you keep adding things or adding more things, and not in cases where you remove it. Like the Gmail scenario, we don't want to remove elements. Right? Once if a user deletes the account, that account is not available, and that's about it.
Okay. Yeah, that makes sense. Thanks.
Awesome. Any questions? So I'm going to just post the fourth question and move on. We're not going to discuss it, which is how will you apply the concept of Bloom filters in the find duplicate question, which is basically finding a missing element, which is finding a duplicate element instead of a missing element. It's something for you to think about. I don't think it's just interesting variation. So think about it. Let's move on to the next question, which is interesting in its own way. Is if I give you an unsorted array with only positive numbers, I want you to return the smallest missing number. It's a extension to the find missing question, but what I'm asking for is the smallest number that's missing.
Use divide and conquer.
How would you do that? I don't follow.
Are you allowed to sort it?
Let's start with yes.
What?
Let's say yes, you can.
Okay.
So for the divide and conquer approach.
No, 1 second, Vishwa. So let's assume sorting. So Pamela, how would you solve it if you can sort it?
Try the midpoint problem and then see how far left you can go after sorting. So basically, you start with, you sort it, you then go for the midpoint, see if there's anything missing on the left. If there's nothing missing, then you have to look at the right side. And then, of course, then you partition from the right side, you take chunks and work your way from the left, just looking at your index versus your number.
So why do we need to look at the midpoint? Anyway, the problem is to find the minimum missing number. So once we have sorted, we can keep looking at the incremented values, and whatever the first missing value is the one.
Well, I was trying to cut the problem down. Because if I look at the midpoint, it'll tell me if anything's missing on the left. And only then can I look into it if there is something missing on the left. See what I mean?
You are reducing the time.
Okay.
Yeah.
Okay.
Yeah.
So binary search can be done in two ways. I think we've had this kind of discussion like in a few situations before. Is that binary search is one is where you know the data set size, you go to the midpoint, you decide whether you want to kill the left half or the right half, and then you keep repeating. Right? That's the binary search that you're talking about. Another way of doing it is doing expanding scope, where you basically what you do is you go to the first element to see if it's missing. If it's not, if the A of I and I are in sync, as in they're the same, then you go look at the third element now. Like you go jump 2 ahead, and then you jump 4 ahead, then you jump 8 ahead, and so on, and you keep expanding your scope of search. And once you find that there's a problem, you just go back to the beginning of that scope, and again you start with a 1 problem, 2, 4, 8, 16, and so on.
That is the bottom-up divide and conquer, right?
Correct. That is if you can sort it. Okay. So sorry, Vishwa. I was thinking that you were looking at a different divide and conquer problem, but if you can sort it, then that's the answer. Absolutely. So we've had this specific discussion about binary search using expanding scope versus binary search with actually divide and conquer in terms of cutting it into half and doing it. So we've done both scenarios. How would you solve it if you cannot sort it now?
So that's the thing, right? If you don't have to sort it, just look at the first 2 elements, right? In this example, right? You look at 2 elements, and you look at so you look at 2 elements at a time, right? And then you look at 4 elements at a time, and you keep going like that. And for each range, you find the missing elements, right? The minimum element that's missing, right?
It's not sorted.
Yeah, it doesn't have to be sorted.
Okay.
Does not have to be sorted. So say.
So no, then repeat this. So in this case, right, we have 9547218.
So you look at 9 and 5, right?
Okay,
So
everything is except 9 and 5.
Right? Yeah, just look
no,
at 9
minimum
and 5.
missing is 0. Minimum missing is 0.
Minimum, so the range is from 0 to infinity, right? So if you look
0
at 9
to
and 5,
infinity, correct. Yeah.
So if you look at just 9 and 5, the missing element that is minimum is 4 and below, right? Or 0, right?
Mm-hmm.
Okay, so that doesn't work. Okay.
Are we allowed to use memory?
Sure, of course.
Or you say this way, right? 9 and 5, it's not the minimum missing, it's like the number below 5, right? Which is 4.
Mm-hmm.
In 4 and 7, the number below 4 is 3, right? 2 and 1, the number below 1 is 0. 8 and 0, there is nothing missing, right? Then you go the next.
No, 8 and 0, the missing number is 1.
There cannot be anything below 0, is what I'm saying.
But it can be something above 0 that is missing. Between just if the data set given to you was 8 and 0, the missing number is 1.
Oh, I see what you're saying. Okay. Okay.
Brute force way, create a hash set, go through the array, stick everything in the hash set, then go again. In your hash set, find the smallest number. Obviously, we're going to start it in a range. And then starting at, so you can put an iterator on the hash set, and you can find the smallest number. Then you set your I to that, and then you just keep fetching from your hash set. When you can't fetch, that's your first missing.
Anyone has any questions with that approach?
I was just curious, are the positive numbers always from 1 to n in some sense?
Positive numbers by definition are 0 to anything, not n, but 0 to 64-bit integer.
So do you think having a bit vector here would be very expensive or something in terms of space?
Yes, Priya, 64-bit, right? If you want to have a bit vector that actually covers such space, that will be as I think we talked about in the previous case, right? It will be in petabytes.
Right.
And
so
is
having
it
a bit,
possible we can use find the maximum number and find the minimum number, and then we can find that which is the missing minimum number.
Got it. Who's speaking?
This is Purna.
Hi, Purna. So yes, so that was an interesting twist, right? So I think Pamela mentioned that as well. Is that let's assume that you, for whatever reason, you had like all the numbers in the set are like 1 million and above, or you've got lots of numbers and you just don't know where you want to know where to start and where to stop. Like you don't want to just keep going from 0 all the way up to million or something like that. It doesn't make sense. But is there a clever optimization? Is there like a better tricks that you can actually apply? Is there like a way of minimizing the number of searches that you will do?
So I missed the previous solution. So what was the hash set solution that was suggested?
You take all the elements you have, stick it in a hash set, and then you essentially figure out whether you have, then you figure out, you know what the smallest number you have is. When you're actually sticking it in the hash set, you're also trying to figure out what is the smallest number you have and what is the largest number you have. And then you're just using that to search. So if you know that the smallest number in the hash set is 1 million, then you know the zero's answer.
Okay.
Right? If the smallest number in the hash set is 0, which is good, then you start looking for 1, 2, 3, 4, and you keep going all the way, and you find the answer. Right? That's kind of the basic answer. One interesting element. Go on.
You can find the sum and then subtract it from the sum here, n into n plus 1 by 2, and then whatever the number you get, you can basically it is probably the addition of the missing numbers. So you can search for all the numbers from 1 to that number, I guess, if it's there in the hash set.
No, if there are multiple missing, then you will not be able to use math to find out.
Okay, so
if only one number is missing, then you can do math.
Oh, right. So yeah, correct.
Yeah. So one thing is that Hashmap solution, I mean, if you're keeping track of only minimum and maximum, so you could wind up with a minimum of 0 and maximum of the 64-bit integer size. So you might end up looking at the entire possibility, the whole thing.
Correct.
So how about and that's like a lot of space. So how about this? If we use that kind of solution which we used where we didn't have sufficient space, I think for the second problem where we were trying to find duplicate. So I mean we created a hash map of size 10, right? I mean the memory size, whatever, and we did 10 elements at a time. So we can do something like that again over here. So we can create a hash map, like for instance, say again 10. And,
actually, a hash set suffices, but okay.
Yeah, right. Hash set. I mean, yeah, any hash table. So I mean, even if duplicates are there, we are not worried. We are just looking for the missing number, right? So 1 to 10 is pretty small. So we can keep track of whether we've by creating the entire array, whether we've covered all 0 to 10 or not. If not, like in the previous case, we can move on to 10 to 20 or something like that.
Right. Just like you do the find duplicate, you can do the find missing in the same algorithm, the multi-pass, right? Yes, you can do that. It's a very simple. I mean, I'm glad that you're actually taking an existing solution that we have discussed now or earlier, and you're trying to apply that to a new problem. And in this case, it actually is a good solution. I mean, considering a few other constraints, if I toss in a similar looking constraints, that is the only viable answer in that case. Now, we still have more constraints which are not there, right? So we have some constraints which actually enable us, like sorting this array. If I permit that, then you can do sort and just do a divide and conquer kind of a scan. Or if I stick the whole thing in a hash set and then figure out what is missing. So one of the curious observations I have is the missing number is always is either 0 or it is a of I plus 1. Of the form a of I plus 1. It will be one more than an element in the array, right?
Can you elaborate on that? I didn't understand how it's a of I plus 1.
It will be one more than an existing element in the array by definition.
One more than an Okay.
Right?
Okay.
So what you can do is that what you'll do in this case is that you could actually keep a heap.
Okay.
Of k plus 1, as in whatever element comes. So first, what I'll do is I'll take 9, and I'll put 9 plus I'll put 0 in the heap, as that's the top of the heap, which it's a min heap. So the smallest element will be in the top, right? Then when 9 comes, I can put 10 inside the heap because 10 is the other candidate for the smallest element, right? Now 5 comes in, then 6 is a candidate for the smallest element in the array as well. So your smallest element could be either 0, 10 or 6. Like 7 cannot be a smallest element at this point of time because 7 or 8 cannot be the smallest elements because all you have is a 5, right? So since there's a 5, 6 is the smallest element that's possible.
No, but like you said, you are you're restricting the heap size to k plus 1. So k is, I'm assuming, a much smaller number than n, right?
No, I'm not restricting the heap size. I'm just putting k plus 1 value in the heap. So I'm putting 9 plus 1, 10 in the heap. That's all. I'm not restricting the size of the heap.
It means k is AFI, not k is not the number.
Yeah. Okay. I'm not restricting the heap. I'm just putting the next value. So if 9 comes, I'm putting 9 plus 1, 10 inside the heap. Okay. If 5 comes, then I'm putting 5 plus 1 inside the heap. If 4 comes, what I'm doing is I'm actually trying to, so 4 plus 1 is 5. I will have a hash set as well that actually keeps track of the elements that I have seen so far. Check if 5 is in the hash set. If it's already in the hash set, then you do nothing. You put 4 in the hash set basically. Then now you have 7. Since it's 7, I check if now my next element, I have to take 7 and put it inside the hash set, and I'll put 8 inside the heap.
So once you're done
It's a
with
bit
all
of
this,
a
you keep copying until you find an element which is not in hash set?
That is correct. So when it comes to the last element in this case, right? So when I come there, I look at 0. 0 is at the top of the heap right now, so which means I can evict 0 from the top of the heap, right? Then 1 will be the top of the heap. Then I'll evict 1 from the top of the heap, and 2 and so on. I'll keep evicting whatever is there at the top of the heap till I find a number which is 3 in this case, which will be at the top of the heap. So my heap will contain 3 and 10. That's it.
So is this the solution takes O of n space?
This solution will take O of n space for the hash, and it will also take a O of, potentially worst case, O of n space for the heap as well.
Yeah.
Okay, so it is O of n space, but what it does is that it actually keeps the operation is actually incremental in nature. This kind of a complex data structure munging, what it does is that as and when new data comes in, you can use that to figure out what is the smallest element so far.
Mm-hmm.
Right, so if depending on the problem space, this might be a solution. I'm just giving you like a weird way of using a combination of a heap and a hash map to keep track of existing elements and missing elements.
But is this better than the sort and binary search solution? Because the heapify also takes like n log n, right? It's almost like a heap sort kind of thing.
Yes, but in the worst case, yes. In the average
yeah,
case.
I agree that this is online algorithm, right? You can work on dynamic sets, like as the inputs are coming in, you can work on that.
Correct, and you don't necessarily. That's basically why this algorithm is like a little interesting to me is that if I look at this, I can keep dynamically keeping. I can keep I know what's missing, and I can just keep that computed and ready, and then I can just evict as it goes, and at any point of time I'll be able to answer this deterministically whether it's there or not, right?
Okay, but I mean, if you have a static data set, then it's as good as sorting and binary searching, right?
Correct, absolutely. Again, most of the solutions actually are directly dependent on the constraints that are placed on you.
Correct.
Right, so it's just that. So anyway, we've got like about a few more minutes. I want to introduce the next problem, and we may not end up going through that in its entirety. And we'll see if we can either pick it up the next one or later. But any questions on this problem before I move on to the next one?
So can we just summarize that the smallest missing problem once?
Sure. The smallest missing problem has a bunch of solutions. We discussed the sort and binary search as an option, which works very well for certain constraints. Then we also discussed a solution where we could do the multi-pass approach, where we do the ranges by ranges, and then we can just go keep doing it. That's the same that we discussed for find duplicate. You can use the same thing for find missing. The third solution that we discussed right now was where you use a combination of a hash and a heap. The hash set stores the elements that you have seen already, and the heap stores the elements that are potentially missing, which is essentially one more than the elements in the hash. Before you put an element inside the hash, you just check if that element +1 is also in the hash. If not, you can put it in the heap. And this approach will give you a heap that contains a min heap, which contains a list of all the possible missing numbers. And then since it's a min heap, the top of the heap will contain the minimum number.
Okay, thank you.
But what if you? Well, okay. If you find it later, of course you can evict it, right?
You will be evicting it as you go. But the problem is that it's only possible missing is because your eviction is only at the top of the heap, not underneath. So once you evict the top of the heap, the new top, you have to recheck if that is already there in the heap, in the hash, and continue evicting. So one eviction could essentially result in like 10 or 20 evictions.
Gotcha.
Because you're doing it that way. This mechanism offers the ability to not just get you the find smallest missing, but also find the 10 smallest missing, or find 20 smallest missing, find 100 smallest missing, right? If that were to be your question, then it's very very easy to this one actually lends you for that one,
more
right?
flexible and generic.
Correct. So there is one of the questions I got was, so if an element is in the heap, it is found in the array, then do you delete the element from the heap? Like, not right away, unfortunately, because we only have access to the top of the heap, so we don't delete the element right away. So for example, in the first case, right, we put 9 plus 1, 10 inside the heap, then we push, but 0 is also in the heap anyways. If the next element that comes out is 10, then we will not delete the 10 from the heap right then.
You
What
just
we
stick it
will
in the
do
hash
is
set.
we stick it to the hash set and we wait. Once 0 is evicted, the next element that tries to get evicted is the 10 would come at the top of the heap, and then you try to evict that.
Got it.
But yeah, that's I think that's a poor example, because once 0 is evicted, 0 was evicted because you found 0. So what will happen is that as a part of that, you will push 1 into the heap. So 10 will not get a chance to get evicted right away in this case. But the concept is similar. Nanya, does that make sense?
Yes.
Yeah. So yes. So in this example, when 0 is evicted, only then we are actually evicting everything else. So essentially, your heap at the time of 0's eviction will contain all the values from 10, 6, 5, 8, 3, 2, and 9. That will be your heap in this example. This is a terrible example that way, because it actually every element that you have plus 1 is in the heap right now. And once 0 gets evicted, yes, this is only because 0 is the last element. So once 0 is evicted, the next top of the heap is 1, which will also be evicted. The next top of the heap is 2, which will also be evicted. The next top of the heap is 3, and that's the answer. It is unfortunate that the problem set is set up in that way. But in a typical case, that's not what will happen. Right? Given that we have a little bit of less time, I want to take the equitable distribution to next such a session. But there is another solution for this one, which actually involves like keeping range of numbers. So what you would do is that you would actually keep a set of range of numbers. It's more like, so you would actually say that I have 9 to 9 available in this array already. And 5 to 5 is available. And once 4 comes in, you will essentially say 4 to 5 is available and 9 is available. And then you will essentially keep, instead of keeping the element in the hash, what you're keeping is like you're keeping the range of available element. You're just saying that all numbers from 1 million to 1 million, like 10,000 is available already in the hash. So when a new element comes in, it could be one of 3 scenarios, right? It could either be attaching to an existing range, either to the left or to the right, or it could be bridging 2 ranges. So if I have a range of 1 to 5 and a range of 7 to 9, and 6 comes in, what that means is that now you can combine those ranges, and now you can say I have all the elements from 1 to 9. Does that make sense?
Mm-hmm.
And you could use that as a data store to store this information, and then essentially your very first range, either left of the first range or right of the first range, is the answer that's missing. Make sense?
Mm-hmm.
Yeah,
that's another approach.
That is like a lot complicated, right? Because each element could be creating a new range as well. So there are like 4 possibilities we are looking at.
Yes, but depending on the nature of the data that you have, that might actually be a pretty neat solution, where you have if your array is inverse of sparse, as in it's it's fully there, but with just some elements missing, then that's probably the better approach in certain conditions and constraints.
Okay.
There are no solution handouts, Nanya. I don't do solution handouts, because the questions and the discussions are actually very dynamic. And we did that last time because we just try different things. We tried that, but I don't generally do solution handouts. So take notes, send the notes back. We are actually composing the notes and putting them back in the blog. We've done that for some of the older sessions. Haven't done it for the last few sessions yet. All right. got like 1 more minute before we close the session. Any further questions on the fourth question?
Vivek, I was wondering if we can just spend a couple of minutes on this question again, where we create the heap. I'm not very sure I exactly followed. I'm sorry, but so like for the given array, so we are looking at 9, 5, 4, 7. So are we inserting 10, 6, whatever whatever is the value, we are inserting that value plus 1, right? So
Correct.
we are inserting 10, 6, 5, and so on.
10, 6, 5, 8. Yeah, that's what we're doing. Correct.
Yeah.
So
But
we
you do
won't
not
insert 5, right?
because it's already there, right?
Yeah, we won't insert 5.
We won't insert 5 because before you insert the 4 plus 1, you will check if it's in the hash and it is there. If it is there, had it been in the other order, right? Had it been 4 and 5 instead of 5 and 4, then you would have inserted 5. Then you would have inserted 6.
Okay. No, but I did not insert 5, right? I inserted 10, 6, and then I inserted 5.
In the heap, but in the hash, you will put 9, 5, and 4.
Okay. I think I've missed the entire solution. So we are parallelly putting all the elements into the hash as well.
Correct. We will have two. We have two. We have two data sets. One is a hash, which actually stores the elements that you have seen so far, which deterministically tells you whether it's there or not. And you have the other data set, which is the heap, which stores what are the elements that are possibly missing. And depending on how your incoming data comes, you will be creating. You will have it's possibly missing, not just definitely missing, because there would be some of unevicted numbers in your heap because they came later in time.
Okay. So like when we encounter 4, we put 4 into the hash set, but we do not put 5 into the heap. Is that what you're saying?
When we encounter 4, we put 4 in the hash set, but we do not put 5 in the heap because 5 is already in the hash set.
Right. Okay. So then we move on to the next element, and at the end of the whole thing, so okay, I don't want to hold everyone up. I'll probably go over
take what I would encourage you to do is to like draw this out on a paper and see how the heap actually will look at after every step, like heap and hash. How will they look at the end of every step? I mean, again, this is by no means a perfect solution. It will get the job done for sure, and it will also help you, in terms of it's like more of a as Arun was talking, it's an online algorithm in the sense that as data streams in, you are keeping your both your lookup tables like the heap and the hash in the right state of mind. So that actually gives you a pretty decent, quick lookup on both cases.
And the key is that the solution will be in the heap eventually.
Okay.
Well, you have to do some eviction at a certain point.
Yeah, so at what point will I start deleting my minimum element? So like, I mean, I refrained from adding 5 to the heap because it was already there in my hash set. Now, if I encounter say a 6 or say a 5 again, so at that point of time, what happens to my heap? Do I delete the minimum element?
You can only delete from the top of the heap.
Yeah.
And
this
so what
example
you do,
is terrible. This example is terrible because 0 is going to be the top of the heap till the very end, right? That's bad. But let's pretend that the top of the heap was actually not 0, but in this case the top of the heap would have been 10 and top of the heap is 6, right? Now when you get 6, you will evict it. Like if the element that is coming in is the top of the heap element, then you will evict the top of the heap and you will take the current number and put it in the hash.
Okay, and now
and then you have a new top of the heap. You will again test if the new top of the heap is already in the hash or not. It is possible that you left or you missed evicting the new top of the heap because it was underneath when the number came.
Right. And
so one eviction may result in 10, 15, 20 evictions.
Yeah, I could have wound up with a lot of duplicates as well, right? Are the elements distinct?
Elements are not guaranteed to be distinct in this case. Why would you have duplicates? Because once you put something in the hash, you will not put it in the heap again. The heap will not contain duplicates. The hash will not contain duplicates.
Right. Okay, yeah, that makes sense. Okay, yeah, thanks.
Okay.
Okay. All right. So let me park the session for now. I will be up for another 15-20 minutes in case folks want to have any other discussion. Just to wind up the actual conversation as such is that we are running this session every Thursday, Seattle time, 7 to 8:30. So if you have friends who are interested, please spread the word. The more the merrier. You know, we have about 30-40 participants every time. It's always fun to discuss different solutions. We do have in-person class in Seattle on Saturdays. So if you are Seattle based, please feel free to this. Which should be on find the classes. And that's all I have for next week. I think I'm going to start with the equitable distribution question, and I'll probably enhance a little bit more. I am looking at getting on to some kind of strings and arrays based questions as well. So we're going to do the basic data structures for a little bit more time, and then we'll jump on to, I'm looking at getting a design question in the next couple of weeks as well. So we'll get there. So the Seattle one is called Seattle Tech Interviews. So you should go to meetup.com and go to Seattle Tech Interviews. I've pasted that in the chat for folks to see. It has the location. We meet in one of the East Side libraries each week. I believe the coming session, which is this Friday, is in one of
Saturday.
I forget what library. Saturday. It's in, I don't know which library it's in.
I think it's Lake Hills.
Okay, for some reason my internet is a little slow. I'm glad the voice is working, but sure. So please go to the link that I have, and it has the location. All right.
Okay.
Thank you.
Perfect. So I'm going to be online for another 15-20 minutes. If you have any other questions about anything, please feel free to hang around and ask. Otherwise, see you guys next week.
Okay.
Yeah.